Hey everyone, sorry I couldn't be in today, but I thought I'd try to make today a useful day and keep us on track for finishing up at semester. So I'm going to go ahead and do a video for what you're supposed to be learning today. So you can just sit back and listen, and then you can do the discussion at the end. So today we're going to do some notes on uniform circular motion, and then there is a discussion sheet already, or a discussion already posted in Google Classroom. And if you finish that, or if you need to finish the simulation lab, you can do that as well. So if you take a look at this video real quick, what it is this guy set up a peg in the middle of his lawn and tied some rope to a lawnmower. And that lawnmower then goes around in the circle, and it cuts his lawn. And as you can see, there's like a little circular path that the lawnmower is following. So there's this nice little circular path. And there's some questions I'd like to ask you about that. How would you describe, if you checked out this video or if you could just imagine it, first question is, how would you describe the speed of the lawnmower? So if you cut the lawn, you know this already, but the speed of the lawnmower, even when you're turning, and even in this video as it's turning, it's constant. The speed is constant. It's going at a constant speed. But how would you define the direction of the lawnmower? And the direction is constantly changing. It's moving in a circle, so it's changing. It's always changing. So the speed is constant, but the direction is changing. Well, then the next question is what about the velocity? Well, the velocity is, if we recall from when we first learned about velocity, it's speed with direction. So if the speed is constant but the direction is changing, that means that the velocity also has to be changing. Okay, well, going back to what defines a change in velocity, that's the acceleration. Now the direction is constantly changing, which means the velocity is constantly changing, which means we actually have a constant acceleration. So looking back, we had a constant speed. The direction was constantly changing. Since velocity is speed and direction, the velocity is also constantly changing, which gives us a constant acceleration. So even though we're going at a constant speed, we have constant acceleration. And this is getting us into the concept of uniform circular motion. The speed of a particle or an object going in a circular motion is constant. Since the direction is always changing, then the velocity cannot be constant. And the magnitude of that acceleration is v squared over r. It's the velocity squared divided by the radius. We'll call this the centripetal acceleration. So as we start talking about rotational motion here, the first style is going to be uniform circular motion. And that's an object going around a circle at a constant speed. Now on the right over here, we see that the acceleration is a vector, and the velocity makes sense. It points tangential to the rotation. So if he instantly cut the string, that's the direction that the lawnmower would go. But the acceleration is always into the center of the circle. So the acceleration is into the center of the circle, and its magnitude is v squared over r. So there's some new terms that we're going to need to help us define this. So we're no longer looking at a linear motion. So it's really hard to say, oh, it went 6 meters, because it's just going in a circle. So we actually have a couple new things, new ways of defining what is going on with this type of motion. The first way we're going to look at is we're going to talk about how long it takes something to go around a circle. Now, how long it takes something to go around a circle, we call that the object's period. So if I think about the Earth as it goes around the sun, it takes 365.25 days for the Earth to go around the sun. That is the period of the Earth. But there's also another concept called frequency, and that's how many cycles is made in every second. So if you look at something like a drill might be rotating or spinning at, I don't know, 500 cycles per minute or revolutions per minute. So we can take a look at that and see how many cycles are given in every second, and that's an object's frequency. Now, these two concepts are related to each other, and this formula right here says the frequency is inversely related to the period. So we can use these vocabulary words to explain what something's going on in a circle rather than looking at like how far it travels in a straight line, which is what we did before. So to kind of help us continue to describe the motion that's occurring, we have several ways that we can do this. First off, going back to this concept of velocity. Now, velocity, when we first learned about velocity is a very simple concept. It's distance over time. So how far you go and how long it takes you to do that, like 60 miles in 1 hour, that gets a velocity, which is distance over time. Now, in this case, the distance is actually the circumference of the circle, which is 2 pi r. And the time, oh, that says circly. That's okay. That's a word. The time that it takes to do that is its period, is the object's period. Or 1 over the period, of course, is the object's frequency. So we have different ways of describing the velocity in uniform circular motion than we did with linear motion. And that's something we'll be exploring in this unit. Similarly, looking at the concept of acceleration, we learned that acceleration is v squared over r. So if I take my different velocities, so 2 pi r over t, or 2 pi fr, and plug them in, I get two additional equations for velocity. So we can add these to like our equation bank as if we're looking to solve problems about uniform circular motion, which we're not doing today, but we will be doing throughout the course of this unit. There is one new concept, another new concept that we also have to look at, and that other new concept is we learned in that simulation that we took a look at was angular velocity. This is a different way to describe how fast something moves that's independent of where it is. So if I think about like an object as it goes around a circle, as best as I can draw a circle, it has some instantaneous velocity. But since it's going around a circle, we can also look at how fast it's rotating. And we call that angular velocity. We'll use omega. So how fast it's rotating is angular velocity. It doesn't matter how far away it is from the center of the circle. So I'm going to talk later, I'm going to talk about like if you went to the Six Flags and you got a kid that's terrified of roller coasters, but they are willing to grab the they're willing to ride the merry-go-round, where do you have them sit? And some of you might not have an answer for this, but we're going to talk about that. If you sit on the outside, look at all this circumference that you're covering versus sitting in the middle, look at this circumference that you're covering, and you're doing so in the same amount of time. So if you're on the far outside, you go really fast. If you're close to the center, you actually go slower, but the merry-go-round rotates as one unit, and that's known as its angular velocity. Now, angular velocity is measured in radians per second. Some of you that have taken trig and pre-calc, you're very comfortable with this. Many of you have not taken it, but for right now, all we care about, one revolution is 2 pi radians. That just means 360 degrees is one revolution, which is 2 pi radians. And this will actually relate back to our velocity concept, and we get two final equations that we're going to add to our bank today. Velocity, the instantaneous velocity, this is how fast an object's moving at the outside, is based on how fast it's rotating and how far away it is from the axis of rotation. And similarly with the acceleration, except now the angular velocity is squared. So a couple more things, we're getting all these equations to help us describe what's going on, added to our repertoire. There's a kind of a cool video here. As you can tell, this guy's having a great time. Feel free to check it out. He's going to take a look at going in the human centrifuge. So the human centrifuge, not to be confused with the human centipede, the human centrifuge is a way for you to sit in a chair, and that's what he's doing right here. And it spins you in a circle. And because of this concept that centripetal acceleration is v squared over r, and centripetal acceleration is how fast we're accelerating, they can actually simulate additional or greater g-forces by manipulating how fast this thing is angularly rotating. So he goes in and I think he gets to like 4.6 g's or something like that. And 4.6 g's, all that means it's 4.6 times g, which is free fall acceleration, which as we know, we're lazy, is 10 meters per second squared. So that's 46 meters per second squared, which that's like falling 5 times faster than free fall. So it's quite a rapid acceleration, and it has a lot of crazy effects on the body. And this guy is gonna take a fun little course in that, where he's gonna sit down and see what that's like. So feel free to check out that video. So we do have one last example problem. An audio CD has a diameter of 120 millimeters and spins 540 RPMs. When it's spinning at its maximum rate, how much time is required for one revolution? And if a speck of dust runs on the outside edge, how fast is it moving? What's its acceleration? So this question is just getting us into utilizing our formulas and what we've learned so far. So I'm going to go ahead and start by actually changing some of our numbers here because they're not in familiar terms with us. So first, let's collect some information about the problem. It said the diameter is 120 millimeters, which is a 0.120 meters, but that's actually, the radius is half that, so we get 0.060 meters, and frequency in 540. That's F. That's our frequency. That's in cycles per second, except it gave it to us in revolutions per minute, so we're going to convert it from revolutions per minute to revolutions per second. So we get 9 cycles per second. That's our frequency measured in, right here it's measured in inverse seconds. We'll also talk about the unit of hertz. So it can be measured in hertz. So now we're actually ready to use this stuff. The time for one revolution is 1 over the frequency. So that's 0.11 seconds. How fast is the speck of dust moving? We actually have a ton of different equations we can use for this. I used V equals 2 pi RF or 2 pi FR, and I plugged in what I got, and a speck of dust on the outside is actually moving at 3.4 meters per second, which when you think about 3.4 meters per second, that's actually really, really, really fast. We walk at like a meter per second, but we got a little speck of dust just going around the outside edge of a CD. So it's going quite fast. And finally, what's the acceleration? I'm going to use the same formula, except it's going to be squared. For the acceleration formula, I plug that in, and it is 190 meters per second squared. And that is insane. That's 19 G's right there. It's huge. So that's why the human centrifuge is so effective. By causing that change in direction, that causes that centripetal acceleration, which is quite large. So that's actually it for today. So you got just a discussion to tackle with your partners or your friends, and that is on Google Classroom. And we will be back tomorrow with some additional, or continuing to learn about this concept of circular and rotational motion. And we'll see you then.